Okay, welcome back. This is lecture 17. In this lecture, we'll be looking at some of the consequences and applications of the singular value decomposition that we showed in the last lecture. Okay, so our first consequence is we get something called the polar decomposition. Okay? So this is a decomposition that works for any square matrix A with real entries. Okay, so if A is a square matrix n by n, then we can do the singular value decomposition on it, right? And we'll get this. In this case, U and V will both be square in this case, n by n, still orthogonal. And now the sigma will be a proper diagonal matrix, right? Not just a fake diagonal matrix. It'll be a proper diagonal matrix because it will be square as well. So along the diagonal of sigma, we'll have the singular values up to sigma r, where r is the rank of A. Okay. Now we're going to do a little trick here. Okay. We're going to observe that V transpose V is the identity matrix, right? Since it's an orthogonal matrix. Okay. So I'm going to look at my equation here, singular value decomposition, and I'm going to just write in V transpose V right here. Just put it right in there between the U and the sigma. Okay. Since V transpose V is just the identity, I'm allowed to do that, right? Now, I'm going to rearrange the bracketing of the matrix multiplication. So I'm going to bracket off the first two and bracket off the last three factors. Right? Since matrix multiplication is associative, this is allowed. I can bracket it off as I like. Now I'm going to examine this new form of A that I have here. Okay, so let's look at the second factor first. Okay, so examine V sigma V transpose, and we notice that this is of a special form we recognize, right? This is an orthogonal matrix times a diagonal matrix times the first orthogonal matrix transposed, right? And we remember this, right? That's the form of orthogonal diagonalization, right? By the diagonalization theorem, that means that this product is actually a symmetric matrix, right? So we can rewrite this part here as S, symmetric matrix. Okay, so let's examine the first factor here, U times V transpose. This is orthogonal times orthogonal, okay? And there's a fact that product of two orthogonal matrices is again orthogonal, okay? I don't think we prove this, but it's not too difficult to show. It should be believable, right? Since an orthogonal matrix is a rotation. So a rotation and then a rotation is again just another rotation, right? So this first factor here is going to be an orthogonal matrix. Okay, and we'll label it Q. Okay, so this construction of Q and S actually gives us a nice factorization of A. Okay, so remember this part is Q, this part is S, so A is Q times S. Okay, so here's the theorem. Okay, if we let A be a square matrix, then A has polar decomposition or polar factorization, A equals Q times S, okay? Where Q is an orthogonal matrix and S is symmetric, okay? So we actually know a bit more about S, okay? We know that it's going to be either positive semi-definite or positive definite, okay? Why is that? Well, this is what S was, right? And this is its orthogonal diagonalization. So that means its eigenvalues are on the diagonal of the sigma here, okay? And the sigma has this form, right? And since the sigma is coming from the SVD, we know a lot about the singular values, what they can be, right? They're all real numbers, right? And sigma 1 through sigma r are positive real numbers, and there's possibly some zeros here. Okay, so we know the eigenvalues of S. Okay, so if A is invertible, that means the rank of A equals n. Okay, that means we'll get all positive eigenvalues filling up the whole diagonal here. Okay, and so S will be positive definite. If the rank is less than n, then it'll look more like this matrix here. It'll go up to sigma r, and then there will be some zeros. And that will mean it's not invertible, and it's only positive semi-definite. Okay? So you may recognize the word polar here from complex numbers, where we have the polar version of a complex number. Okay? And that's not a coincidence. This factorization, in fact, sort of gives an analogy between real matrices and complex numbers. Okay, so let's just recall this these facts about complex numbers. Okay? So if we have a complex number z, right, then its polar form was like this. We write z equals r times e to the I theta. Okay, so if w is another complex number, then the effect of r, this number, times w is a stretch of w. Okay, and the effect of multiplying this other part, e to the I theta, times some other w, complex number, is a rotation of w by theta. Okay, so a complex number can be factored into its stretching part and its rotation part. Okay, so it's very similar to what we just did, right? So that's the sort of analogy here. Okay, if A equals Q times S, where Q is orthogonal and S is positive definite, okay, then a positive definite matrix can be seen to sort of stretch the space, okay, and the orthogonal matrix rotates the space. Okay, so that's the analogy here between real invertible matrices and complex numbers. We can break it into its stretching part and its rotation part. Okay, that's summarized here. Both complex numbers and invertible real matrices can be factored like this, and this is their polar form, their polar decomposition. So you might ask, if we have the SVD like this, which is orthogonal, diagonal, orthogonal, now what's the difference, or what's the advantage of writing it as orthogonal times, symmetric, positive, semi-definite? Okay, so there is an advantage to looking at it like this. The advantage is that it cleanly separates A into two factors, and all the stretching is done in one factor, and all the rotation is done in another factor. Okay, and doing it like this has, the nice analogy with complex numbers. It also has an application in continuum mechanics. Okay, so continuum mechanics, studies materials and how they react to being compressed and stretched. Okay, so in this field, the factorization Q times S is very useful. Okay, so if you're studying the deformation of a material, then it's important to cleanly separate the stretching from the rotation. Okay, and A equals QS does exactly this, right? So the reason it's important is because under rotation, the material doesn't undergo any strain or stress. Okay, so under the Q part, the material undergoes no strain. Under the S part, which corresponds to a stretch or a compression of the material does undergo strain, which is proportional to the eigenvalues of S and in the direction of the eigenvectors of S. Okay, so that's an application of this particular factorization that's useful in material studies. Okay, so now we'll turn to the situation of A being an m by n matrix, so a potentially non-square matrix. And we'll talk about what I'll call the pieces of the singular value decomposition. Okay, so these pieces will be very important in applications of the SVD. Okay, so this is the situation. Okay, A is m by n. So we have singular value decomposition like this. U times sigma times V transpose. U is m by m orthogonal. V is n by n orthogonal. And sigma is m by n almost diagonal. Okay, and the singular values along the diagonal of sigma will be sigma 1, sigma 2, all the way to sigma r, where r is the rank of A. Okay, and we always order it like this, right? Where sigma 1 is the highest one, sigma 2 is the second highest, and sigma r is the lowest. Okay, right? And we know these numbers will be positive and real. And when we label our U's and our V's, we like to separate the first R from the remaining singular vectors, like this. Okay, so right, the first R correspond to these singular vectors, these non-zero, and the remaining ones correspond to the singular vector 0, if it's there. Okay, so what can we get just by writing the SVD in a different way? So here is A. I just write out U as columns U, and I write out sigma like this, and I write out V transpose. So the V's are now rows. So if I multiply the first two matrices, I get this. Okay, notice that everything past UR just turns to 0, right? Because it's associated to the singular value 0, right? So they just, all this just disappears over here. Okay, and now I want to multiply these two matrices. What I'm going to use is the column row rule for multiplying AB. So it's the same rule we used in lecture 14 for getting the spectral decomposition. Okay, so we'll use that rule here, which says that this A is equal to column 1 times row 1. Right? Column 1 of the first matrix times row 1 of the right matrix. Okay, plus column 2 of the left matrix times row 2 of the right matrix, and so on, and you take that sum. Okay, and when I take that sum, I get this here. Right? It's going to be sigma 1 times U1, so this part, times V1 transpose, plus sigma 2 times U2 times V2 transpose, and so on, all the way up to sigma R times UR times VR transpose. Okay, so since everything past here is 0, we're going to lose the V's that are past R over here. So those ones just disappear, right? They don't come into this. Okay, and so each one of these is called a piece of the singular value decomposition. So now I'll make two important observations about the pieces of A. Okay, so if we look at each U, it's a m by 1 vector, and if we look at each vi transpose, right, it's a 1 by n vector. Okay, so that means ui times vi transpose is going to be an m by n matrix, right? And then we multiply it by the number. That doesn't change the size, right? So each piece is an m by n matrix, and so it's going to be, right, each piece is the same size as A, right? And each of these pieces will have rank 1, right? Remember, from, I think, the first test, we showed that any vector of this, or sorry, any matrix of this form is going to be of rank 1, right? Provided both vectors are non-zero. In this case, since they're singular vectors, they are non-zero. Okay, so each of these is of rank 1. So what can we say in total? Every m by n matrix has a singular value decomposition, right? So they can all be written as pieces like this. Okay, so each m by n matrix A with rank R is the sum of R many rank 1 m by n matrices. Okay, that's a very nice observation we get out of this. So to state the next important consequence of the SVD, we have to define the matrix norm. Okay, so we know how to take the norm, or the length of a vector, okay, but we haven't said how to take the length or the norm of a matrix. Okay, so there's no obvious way to do this. Okay, there are many different ways you can define the length or the norm. Okay, so here are two examples of matrix norms. Okay, so we write the norm by writing double lines around the matrix A. Okay, that means the length. Okay. When we write just one line around A, that means the determinant. But when we write double lines, that means the norm or the length. Okay. So one example of a norm is the L2 norm, and we specify it's the L2 norm by writing 2 here. Okay, and what it is it's the maximum of the length of AX divided by the length of X. So you look over all X's in the domain of A, in other words, all vectors in Rn, and you see what's the biggest possible ratio between the length of AX and the length of X. Okay, so in other words, what's the biggest possible stretching of a vector that the matrix could do? That's one way to define its size. Okay. Another way to define its size or its norm is in terms of its singular values. Okay, so this is called the Frobenius norm, and we compute all the singular values of A, take their squares, take the sums, and then root it, and that's called the Frobenius norm. Okay, so there are many ways to define the norm. These are two of them. There are rules it must follow, like it must be additive and have some other properties. One thing that is not a norm of the matrix is the determinant. Okay, so you can't use the determinant to define the length of a matrix, in particular because it's not additive. Okay. Okay, so the reason we introduced matrix norms is because we're going to talk about approximations to a matrix. And to have approximations, you need to define the distance between two matrices. And to do that, you need to have a definition for the norm or the length of matrices. Okay, so now we'll talk about low rank approximations. Okay, so we'll start with some notation here. Okay, so let A have rank R, and suppose we have the SVD pieces above. So we have R many pieces of A. Okay, now let's consider a number K, which is a positive number, and it's less than or equal to R. Okay, so now we're going to consider this expression. Okay, so A sub K is equal to the sum of the first K many pieces. Okay, so A1 is just the first piece. So just take the first piece, that's it. A2 will be the first two pieces, right? And so on, right? So A10 will be the first 10 pieces, okay? And AR, where R is the rank of A, will be A itself, right? Because if you take them all the way up to R, then it just equals A, right? So AK is the sum of the first K many pieces, okay? And an important fact is that the rank of AK will equal K. Okay? So you're taking the sum of K many rank 1 matrices, and this will equal, or this sum will have rank k. Okay, so in general, when you take the sum of matrices, it's not equal to the sum, or sorry, the rank is not equal to the sum of the individual ranks. Okay, but in this special case for the SVDs, when you sum up k many rank 1 matrices, the sum has rank k. Okay. But that principle is not true in general. The SVD is special. Okay. Okay, so now that we've defined the norm of the matrix, and we have this AK notation, which is the sum of the first k parts, or k pieces, we can state the important theorem now. Okay, so this is the theorem. It's called the Eckhart-Young theorem. Okay, so it says if B is some rank k matrix, okay, then the distance from A to B is greater than the distance from A to AK. Okay, so what's the interpretation of this inequality? Okay, it's saying that the rank k matrix that is closest to A is AK, right? Where AK is the sum of the first k pieces of the SVD. Okay, so let's explain that a bit more. Okay, so what this means is that A1, which is just the first piece of the SVD, it's the best possible rank 1 approximation of A. Okay, in other words, of all the rank 1 matrices, it's the closest. Or more precisely, there's no other rank 1 matrix that is closer to A than A1. Okay, and now you see why we needed this definition of norm, because the norm is used to define the length or the distance between two matrices. Okay. A2, which is the sum of the first two pieces, is the best rank 2 approximation of A. Okay. So of all the rank 2 matrices, A2 is the closest. Okay. And in general, AK is the best rank K approximation of A. Okay. Okay, so now we'll state this important interpretation of what we just said, the low rank approximations from the SVD. Okay, so let's suppose A has singular value decomposition with these singular values. Okay, so sigma 1, so sigma r, ranked as we usually do. Okay. So here are the pieces of A. Okay. And interpretation of the previous theorem is that these pieces are actually coming to us in order of importance, where the first one is the most important piece. The second one is the second most important, and so on. Okay, so why do we say that? Well, sigma 1, U1, V1 transpose, the first piece, that's most important because it's the rank 1 matrix closest to A. Okay? In particular, it's closer to A than any of the other pieces. Okay? Additionally, in when we take higher rank approximations, okay, it always involves the first piece. Okay, so the best approximation of higher rank matrices always involves the first piece. Okay, so that's why we call it the most important piece. And in general, the greater the sigma is, the more essential a piece it is in constructing A. So now we'll look at a visual or geometric interpretation of what the SVD is doing. Okay, so this is the SVD of A. U is orthogonal, so it corresponds to a rotation. V transpose is orthogonal, so it corresponds to a rotation. And sigma only has entries on the diagonal that are non-zero, so it corresponds to a stretch. Okay, so if we think about an x that's in Rn, and we think about what happens to it when we left multiply by A, okay, since A is equal to sigma, U sigma V transpose, then we can break down what happens to x, in steps, right? So the first step is that x is multiplied by V transpose. So the first step is that x is rotated by V transpose. And then the result is stretched by sigma. And then the result of that stretching is finally rotated by U, the orthogonal matrix. Okay. And we can visualize this or draw this easily when A is a 2 by 2 matrix. Okay, so there's two singular values and two V's and two U's, left and right singular vectors. Okay, and we can track what happens or study the effect of A by tracking the unit circle and tracking V1 and V2. Okay, so we're going to see what happens to the unit circle under the effect of A. Okay, and that's the same as thinking about a vector x in Rn, or in this case R2, and seeing what happens to it after you multiply it by A. Okay, so as we showed up here, since A factors into U, sigma, and V transpose, we can study the effect of A by studying these three operations in this order. Okay, so this is what we're going to do. We're going to draw the unit circle in R2 here, and we're also going to label V1 and V2, those left singular vectors. Okay, so the first effect is that we multiply by V transpose. So this is going to be a rotation of the space, right? So let's see what it does to V1 and V2. So if you take V transpose and multiply by V1, okay, you'll get 1, 0. You can check that, right? And that's equal to the first standard basis element. And similarly, V transpose times V2 will equal 0, 1, or E2. So what is V transpose doing? Okay, so it's taking V1 and mapping it to E1, and it's taking V2 and mapping it to E2. So the rotation it's doing, right, it rotates the plane by some angle, and that angle exactly moves our V's into the position where the standard bases were. Okay, so that's the effect of V transpose. Okay, and now we're going to do the action of sigma. Okay, so sigma is a diagonal matrix, and it has sigma 1 and sigma 2 on its diagonals. Okay, so when we compute the effect on E1 and E2, these are the vectors we're tracking now. Okay, so sigma 1 times E1 becomes sigma 1, 0. So it stretches this vector out to sigma 1, and it stretches E2 out to sigma 2 like this. Okay, so to be more precise, this diagram should say E1 times sigma 1 and E2 times sigma 2. It should equal these vectors here. Okay, and we have one more operation, right? We're going to multiply these vectors times u. Okay, so u is a rotation, okay, and let's see what u does. Okay, u times the sigma 1, 0 vector becomes sigma 1 times u1, and for the second vector it becomes sigma 2 times u2. Okay, so in total we've tracked A, this is A, right, times V1, and we got sigma 1 times U1. That's exactly what we want, right? That's the relationship between the V, the sigma, and the U. And the same with the second vector too. So that's good that it works. Okay, so let's look at what happened here. So we started with a unit circle here, and the overall effect that A does to this unit circle is it rotates it and then stretches it. Okay, and by breaking it down, we can see exactly how it rotates and stretches it, and we can see how the singular values and vectors are involved in that rotation and stretching, right? Okay. Okay, so what's the lesson of this diagram here? Okay, so we looked at, or we tracked the unit circle and how it was transformed by A, right? In tracking the unit circle, it tells us how A behaves on the whole space, okay? The reason is, since A is linear, that means how it behaves on the unit circle can be extrapolated to how it behaves on the whole space, essentially. Okay, and so what it does on the whole space is it rotates it and then it stretches it like this. So this unit circle turns into this ellipse. Okay, and by breaking it down like this, we see exactly the rotation, we see exactly the stretch, and most importantly, we see how the left and right singular vectors are sort of involved in this. Okay, so if you look carefully at this ellipse, right, it's been stretched by a factor of sigma 1, the first singular vector. Okay, and after the final rotation, the direction it's being stretched in is what? It's the direction of u1, right? The first right singular vector, right? So A is deforming the space in a certain way, right? And it has certain axes of deformation, okay? And the axes of deformation are exactly the singular vectors. Okay? This is an axis, right? It's an axis of the ellipse. And there's also the lesser deformation, which corresponds to U2 and sigma 2. So this is the lesser deformation. In fact, it's, right, from this diagram, it looks like sigma 2 is going to be less than 1, right? Because it's actually compressing or shrinking the space, right? Okay, so here's the important takeaway fact from this. Okay, so you remember that when we talked about the pieces of the SVD, okay, the greatest singular value, sigma 1, corresponded to the most important piece of the SVD. Okay, same thing's going on here. Okay, if we think about how A transforms the space, okay, then the first right singular vector points in the direction of greatest deformation. Okay, so right, the axis or direction of greatest deformation is along here, which is exactly the direction of U1. Okay, so the biggest stretch is sigma 1, and it's in the direction of U1, the first right singular vector.